Hi everyone, welcome back to Royan Study Corner. I am Royan and the aim of this channel is to make learning as fun, easy and accessible as possible. Now in today's video we're going to be learning about graphs. Early on in our lives we would have learned about block graphs and bar graphs, and now we're just going to build on a line graph. Now while we don't actually call it a line graph when we're doing it in school, it's kind of essentially what we're doing. So question 1 of our paper 2 is usually a graph question. So we usually have a table of values, we plot that graph, we find the gradient, we usually use the gradient then to calculate some other things and state the significance of the gradient. And unfortunately it's something that a lot of people struggle with. They come up with a scale, realize the graph doesn't fit, erase it, try another scale, realize it may not fit, erase it, and try and find another scale. So today we're going to go through a method of planning your graph and plotting your graph so that it's done in one go. And once you plan on your scale, you're good to go. You don't have to erase and redo, and everything will work out fine. So I'm going to plot it with you at the same time so you'll see the thought process and how I actually go through it, so that you can just follow along and try it for your graph and see if you like that method. Now it may not be for everyone. I know everyone has their different thing that they like to do, so just check it out and see if you like it. So let's get into it. So before we really get into it, let's just take a moment to think about what exactly is a graph. So a graph is a diagram showing the relationship between two quantities. So even when we were doing or learning about block graphs and bar graphs, they really were showing us maybe the amount of snacks eaten or the amount of people that did something, and they always compared. And that is exactly what we do in these graphs here for physics, and the same for your graphs for math. It's going to show the relationship between two quantities. Now, if we know what a graph is, let's think about why we use graphs. Graphs give us the total picture. You may have just some values on a table and it's kind of hard to visualize or conceptualize what exactly is going on with that data because it's just random numbers and it can be a little bit difficult to figure out what's going on with it. But if we plot a graph with that data, then it kind of gives us the big picture. We can identify relationships and patterns and be able to see, is this increasing, is this decreasing, is this constant? We can identify any data or observation that may be wrong. So sometimes you're plotting a graph and you realize one particular point is way off. Then you know something went wrong there. There was some error during the lab, or maybe you accidentally took down the wrong value, something like that, because it just doesn't make sense for that value to be so far away from all of the other values. We can predict results that have not actually been measured. So if you have a graph and this is your graph paper and you have your graph like this and your points are like this, you can say, okay, I can see the trend of this and then figure out what this is like at this point, even though we don't have a point for there. Or we can extrapolate, which really means they may ask us, okay, what will happen now when we have this value equal to up here? We wouldn't have tested it before, but we can look at the trend and know what would be the general area that would be in. So there is value in using graphs, even though it may seem a little bit tedious. So we know what it is, we know why we use it. Let's look at some of its components. Now a graph can be thought of as two number lines that are intersecting each other. If you look at it, it's kind of like a junction of number lines where x is one number line and y is one number line, and they're meeting in the middle. So your x-axis is your horizontal axis and your y-axis is your vertical axis. The origin is where they meet in the middle. So the origin is the junction or where they intersect. You'll get very used to these terms and you'll realize it'll become like second nature. So x-axis is our horizontal axis, meaning it's going the same direction as the horizon. If you're on the beach and you look out at the sea, so you're on the shore here, let me draw a seashell here and you're on the shore and you're looking out, you'd see like the sun out here and that sort of thing. The horizon is as far as the eyes can see there, and that is horizontal. So it's a good way to remember what is horizontal and what is vertical. So if this is essentially what your graph looks like, then the question might be, where do the random numbers come from? So then we have to think now about the coordinates of a graph. I just mentioned rather, that you can think of it as two number lines intersecting, or a junction. So it really is two number lines, yes. So we know there would be a negative region and a positive region on each of the axes. But if you think about it in terms of like an intersection of a street, or anywhere for that matter, every place that you look at would have an address. And if we say a store is at the corner of Queen and Henry Street, if we're giving someone directions, we tell them, hey, this is at the corner of Queen and Henry Street. You won't just say it's at the corner of Queen. You won't just say it's on Henry Street, because that doesn't really specify exactly where it is. But you give a specific location. It's the corner of these two streets where they intersect. And that is how we locate points on a graph. And we call this address the coordinates of that particular point. Your coordinates, since it's an intersection between x and y timelines, why am I saying timelines, number lines, then you have to express the coordinate in terms of x and y. So we always write it as open brackets x, comma, y, close brackets. So x gives us where it is relative to the x-axis, and y tells us where it is relative to the y-axis. Now let's look at the different sections here and see if we can really see what we're referring to with that x and y. So remember, it's two number lines intersecting. So we can see here our x-axis, and just like with the number line, it goes 0, 1, 2, 3, 4, 5, and we know there'll be the negative section on this side. And on the y-axis, we have our positive section up here and our negative section down here. Then we should remember from a few slides ago, this here is our origin. So we remember that our origin is where the lines intersect, and our origin is also where x is equal to 0 and y is equal to 0. Because if you look at it, we have on the x-axis 1 here and -1, which means in the middle here will be 0. And if you look at the y-axis, up here is 1 and down here is -1, so in the middle here is 0. So the origin, or the point at which they intersect, is at the point where x is 0 and y is 0. Now, when we're plotting points or reading points off the graph, we always look for x first and then y, because that's how it's written. So if we are looking at this point here now, and we're trying to figure out what exactly is the location or the coordinate of that point, we look along our x-axis, we come down, and then we see, okay, this is in line with 5, which means we can write 5 as our x value, and then we go up along our y-axis, or parallel to our y-axis, and we see that that is where y is 2. It's in line with where y is 2. So then the location of that with respect to y is 2. So that is our address or coordinates for that particular point. This point you'd say is at 5, 2. And let's say we have a point down here. Then we do the same thing. we look at x and we see this point is in line with where x is -3. So that will be our x coordinate. And then we go across and see where it is relative to y, and we see y is also -3. So then this point is where x is -3 and y is -3. So this is how you would find points on a graph, or if they tell you to plot a point, this is how you'll read off from the graph to plot the point. Now you'll notice with the general sections of the graph, we have over here y is positive and x is positive in this region. Then if you look over here, you'll see x is negative down here and y is positive up here. If you look over here, you see x is negative and y is also negative. And if you look over here, x is positive and y is negative. So there are all of these sections on a graph, and you just have to pay attention to whether they're asking you to plot a point that's negative or positive. But remember, it's two number lines, so you just follow it just as you usually would with any number line. So while in math we would use all of these sections, sometimes in physics, this little section here in red where x is positive and y is positive. In physics, this is not actually the case. In physics, we usually only use, that's usually where we stick to. So most of our graphs, you'll realize in physics that it usually just looks like an L, because that's the section of our graph that we really focus on with physics. Sometimes it can go into the negative area, but in most cases, most of your graphs will be in this general area. So as we talked about plotting and whatnot, I just want to show these links here. I'll post them in the description box below. There are a few good resources just to get some plotting practice. If you're really good at plotting, well, you don't need to focus on that. But if you like to get a little more practice, you can go follow the link and get a little bit of practice with it, so that once we actually get to plotting graphs, that's easy and smooth for you. Now, once you get enough practice plotting the graphs or plotting points and being able to read off so that you can do it just like that, we have this 9-step process here for us to go through. Now, this may seem like a lot for an entire 9 steps, but trust me, you'll go through it quickly, and it's just a sort of like a to-do list. And once you go down and you check all of the things off, everything will fall into place and you won't have to be going through a set of trial and error. Now we're going to go through all 9 of these steps together. I'm going to plot the graph with you, but before we start going through them, I just want to give you a little bit of a reminder of some of the things to keep in mind when you're plotting a graph. One is use a pencil with a sharp point. If you prefer to use regular pencils that you have to use a sharpener for, then make sure you have a sharpener and you sharpen your pencils every time before you plot your graph, because the last thing you want is some fat line where you can't really see your points properly. We have to use X or a dot surrounded by a circle when we're plotting points. So in math, we may be used to just using a dot to plot a point, but in physics, we use an X or a dot surrounded by a circle. You should have a graph that cuts more than half of the page both ways. So you don't want a graph that's taking up quarter of your page. Then if that happens, it means you didn't choose a sensible scale. So you always have to make sure your graph takes up a good chunk of your graph paper. Choose correctly between a line and a curve. Most graphs we would plot would be a line, a straight line. Most of them would be passing through the origin as well. But sometimes you'd have a straight line that cuts the y-axis or cuts the x-axis. Sometimes you'll have a curve, and you have to pay attention to how your points look to know, and also just generally knowing the theory, depending on what topic you're doing, to know whether you have to draw a line or a curve when you're doing your line of best fit. And finally, one of the things that we forget all the time, label all necessary parts of your graph. Remember, logically, if someone is going to pick this up and read it, they need to know what they're reading. They need to know what information you're presenting here. And even apart from thinking like this, you get a mark for each of these things. So don't give CXC an excuse to take away a mark for you unnecessarily, because you know what you're doing, but it's just not being mindful and putting the labels. So make sure and put all of your labels. So now let's go into the actual 9 steps to plotting our graph. Our first step when plotting a graph is choosing the right axis. Now, what do I mean by this? I mean, you have to decide which quantity goes on the x-axis and which quantity goes on the y-axis. Anytime you are asked to plot a graph, the first variable mentioned goes on the vertical axis, on the y-axis. So if we are told to plot a graph of temperature against time, the first quantity that they mentioned there is temperature. So temperature will go on our y-axis and time will go on our x-axis. Now in this case, temperature is the dependent variable and time is the independent variable. So you can think of this as, you'll see more of this when we get into planning and designing of labs, but your independent variable is the one that you set. It's kind of like the cause, and your dependent variable is the effect. So you do something with the independent variable, and that's the cause, and it has an effect, and that effect, the quantity that is affected, is called our dependent variable. Now, you don't necessarily have to focus so much on that right now, but what you have to make sure to remember is the first quantity that they mention goes on the y-axis. So let's look at an example. Plot a graph of voltage against current. Now remember, the first quantity goes on the y-axis, which is our vertical axis, and the second one goes on our x-axis. So since the question said plot a graph of voltage against current, it means voltage goes on our y-axis and current goes on our x-axis. So we have that one thing down. Now, our next step is to identify the range. The range is essentially how far the values are spread out. So the size or the, I'm giving a very poor definition here, but it's essentially the span of the values. So if you look at voltage, you'll see that voltage goes all the way up to 1.7. and current only goes up to 0.8. So voltage has a larger range of values and current would have a smaller range of values. Now if you think about how a graph page is, it's a rectangle. We have a long side and a short side. So it makes sense to put the larger range on the longer side of the paper, just so that you have more space on that particular side of the paper. So our values are here on this table. We have 0, 0, 0.45, 0.2, 0.8, 0.3, 1.0, 0.45, 1.2, and 0.6, 1.5 and 0.7, and 1.7 and 0.8. So this is the same graph that we're going to plot now. Now, I would say we can pause here, take down the range or the values so that when we're plotting it together, you know which points we're plotting and you can. What does that look like? If our graph paper looks like this, I may do the little 3 holes, you know, they come with that to put in the binder. Then voltage, we'll put it here, and current, we'll put here. Remember, I for current and V for voltage. Now, the reason why I'm specifically stating this is if the roles were reversed, then you could have just turned your graph paper this side and put the voltage up here and current down here, because it's up to you which way you want to turn it. Generally, most people will keep it this way, but it really is up to you. So a good way of deciding which way you want to do it is to put the quantity with the larger range on the longer side of the graph paper. So we know voltage is going on Y and the current is going on X, and we're putting voltage follow along voltage on the longer side of the paper. What is our next step? Our next step is to put the title at the top of the page and then label the axes. Now our title will be graph of whatever against whatever, whatever versus whatever. In this case, we have voltage and current, so we have graph of voltage against current, or if you choose to put graph of voltage versus current, that's up to you. Now, our axes have to be labeled with the quantity and the unit. And note that it says quantity / unit. So if you choose to write the symbol or the word, it's up to you. So you can choose to put voltage / volts. You could put voltage / volts, or you can do it like this where we have a mixture of both. Or you could put current / ampere, or you can put current, and remember, if we think back to fundamental quantities and SI units, current is represented by I, so current / ampere, or we can do this kind of mix here. It's up to you which way you choose to write it, but you just have to remember that you have to write quantity / unit. So everything is labeled here. We have a good little plan in our heads. Now the next step, and probably one of the most difficult parts, is to choose a scale. Now your scale should allow the graph to occupy more than 3/4 of the graph paper. Remember, we don't want a tiny graph in a corner of the graph paper. The scale should be easy to read, meaning we shouldn't have to be trying to figure out 3.336 or any sort of weird values like that. Now, in order to make the scale easy to read, we tend to stick with convenient intervals. So I always advise students to stick with things like 0.1, 0.2, 0.5, 1, 2, 5, 10. These are really easy to work with. Now, I know some students may say, okay, 4 is an even number, that should be easy to work with, or 8 is an even number, and that may be so, but it can make finding points and dividing to get these smaller intervals a little trickier, and it just means you have to focus a little bit more and make sure you're counting properly. So if you can do that well, all power to you if you want to choose those, but I always advise people to stick with these particular intervals and avoid, like the plague, scales that count in 3s, 7s, and 9s. Now you may be wondering, well, how then do I choose what scale is right for the values that I have to plot? Now I feel to say something corny like, I'm glad you asked. So a formula that I teach is to figure out what scale you want to use, and I was taught this by my Form 4 and Form 5 physics and chem teacher, is you calculate your range divided by the number of 2 centimeter blocks on the axis. Now we know our range for voltage was 1.7 and our range for current was 0.8. Now, why are we dividing it by the number of 2 centimeter blocks on the axis? Now remember, you might be wondering, why are we dividing by 12 for voltage? What's the significance of that? This is our graph paper here. Our intervals are going to be generally 2 centimeters. So you have one here, so that you can know what interval to use on your axes. It's from graph book to graph book, but most graphs have 12 2 centimeter intervals on the long side of the paper. So we'd have here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Now notice my graph paper here has 13, but I'm still leaving 12 because I know most people's books have 12. So we divide our range 1.7 divided by 12, and it gives us 0.14. Now, what does this mean? How does this help us? It means that in order to get your graph to fit on the graph page, every 2 centimeters must be equal to a number that's larger than the number that you just calculated. You just calculated saying you'd have 1.4 here, 2.8, which we know is not a good interval, but we're saying that this is the minimum in order for our entire graph to be able to fit here. So if we know that this is the minimum, it means that we have to choose a scale that is larger than this for our graph to fit. And we can say, okay, if it has to be more than 0.14, what number can I think of that's larger than this, that falls within the values that are good, easy numbers to work with? And if we think back to them, they are things like 0.1, 0.2, 0.5, 1, 2, 5, 10. These are the kind of numbers that make that a little bit easier to work with. We're not rounding up in the literal sense of round to the nearest whole number, round to the nearest decimal point. Instead, what we're doing is thinking, what is a number that's larger than this that I can use, that's easy to work with, and will be able to fit my scale? Now, if we look at 0.14 and we look at the numbers that are good to work with, we'll notice that, hey, 0.2 is larger than this. So then I can use 0.2 on this scale, on this axis rather. And the same thing for the current axis. We divide by 2, because if we come back to our graph, we'll see we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we know in order to figure out what range we have to use, we divide our 0.8 by 9 and we get 0.09. Now we know again this is a weird number to use to find a scale, so we're not going to use this. But what we can do with this is think, okay, what number is easy to work with that is larger than this that I can choose? And if we look at our numbers here, we'll see, okay, 0.1, which means on this axis I could use a scale of 0.1, and we have our scale there. This means that we don't have to try a scale and draw it out and then erase and try another scale to try and get one that fits. We've already chosen here what our scale will be, and everything we know will fit because we did our calculation here to see what the minimum needs to be, and that's your scale. So now let's plot a graph together and see if all of these things make sense when we put them together. So I'm going to do a little recap as I am plotting the graph. Now, first thing first, we said that I forgot to mention the values, to go back to the values over to our graph. Now, we said since we're plotting a graph of voltage against current, it means that voltage has to go on our y-axis. And since voltage had the larger range, because remember voltage had a range of 1.7 and current had a range of 0.8, we're going to put voltage on the long side of our graph. So bear with me a minute while I try and pull out my ruler and see if I can make this graph look a little bit decent. So I have one axis, and so the one that I just drew would have been my x-axis, and here we have now our y-axis or voltage axis. Oops. Now my line does not look very straight, so I'm sorry, but we'll have to live with that. Now when you're doing this on your graph paper, we can't live with that. We have to do it properly on your graph paper. But yes, so I have my axes here. We already decided what is going on what side. Now we have to make sure and label. When we're labeling, we make sure to state our title. So we have graph of voltage against current. I make sure and label this axis, so I have voltage slash V. I have down here current slash amp, and I'm going to write in my scale that we just figured out. So my scale is on voltage axis, 2 centimeters represents 0.2 volts, and on the current axis, 2 centimeters represents 0.1 volts. So now let's plug in our values on the scale. So here we have 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and 0.8. Now on our voltage axis, we'll have 0.2, 0.4, 0.6, 0.8, 1.0, because remember it's intervals of 0.2, so we're counting the same way as we did when we were doing our reading scales activities. So 1.2, 1.4, 1.6, 1.8, 2.0. So this is what our graph looks like. So we've labeled everything out, and now remember this is our origin here, where y is 0 and where x is 0. It's just that in this case we're no longer talking about y and x, we're now talking about voltage and current. And I now notice on my current axis I use the wrong unit. So what there should be is amps, because we're not talking about x and y, so we're not saying on y-axis whatever or on x-axis. Instead we're saying voltage axis, and since we have the quantity of voltage, we put the unit for voltage as well, which is volts. So we have all of these things down. Now let's start plotting our graph. Let me choose a different color and maybe a fatter point as well, so you all can see it better. Now I know I said use a thin point, but I'm trying to get you all to see this properly. Now our first point that we have to plot is 0, 0. Now that's an easy one. 0, 0 is right down here. Now the next point we have to plot is where current is 0.2 and the voltage is 0.45. So what do? We look for 0.2 on the current voltage, which is here, and we go up to where voltage is 0.45. You'll notice now that we don't have a 0.45 written on the graph. We have 0.4 and 0.6. So how exactly do we plot that if it's not explicitly written there? We do it the same way we figured out what the reading was when we were practicing reading scales. If we look at the space on the y-axis or the voltage axis, we'll see that from here to here, 0.4 to 0.6, that's a span of 0.2, and there are 10 boxes here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we want to see what the value of each box is, then we'll have to say 0.2 divided by 10, which gives us 0.02. Which means each tiny box here is 0.02, and we can count it out and see if that's true. We'll have 0.4 plus 0.02 is 0.42. So we go 0.42, 0.44, 0.46, 0.48, 0.5, 0.52, 0.54, 0.56, 0.58, 0.6, and we see that that is true because it's fitting there. So then we can find the point 0.45, because we can say, okay, 0.42, 0.44, 0.46. So if we know that here is 0.44 and here is 0.46, then we know that 0.45 will be halfway between both of them. So then what we can do is just put our x in the middle of those two lines. So this is the point 0.2 and 0.45. So you see, even if it's not directly stated on the axis, we can still figure out what the point is. And the same thing works on the current axis as well. We have the same 10 blocks here. And if we know that the distance from here to here is 0.1, then we can say 0.1 divided by 10 gives us 0.01. This means that each tiny box there has a value of 0.01, and we can count that as well to see if it's true. And we'll have 0 here, 0.01, 0.02, 0.03, 0.04, 0.05, 0.06, 0.07, 0.08, 0.09, and 0.1. So we see there that it does work out, and we can just approximate in between values even if it's not actually stated. So let me erase that, and let's go back to plotting. So we have our first 2 points down. Now our next point is 0.3 and 0.8. This will be a pretty easy one because we just find 0.3 here, and we go up to where we see 0.8, and that is our point. So we have this point here. Now our next point is 0.45 and 1. So we have 0.4 and we have 0.5. We have to look for 0.45. Now we already said that everything here is 0.02 and everything here is 0.01. By everything I mean the tiny boxes. So if we want to find for 0.45, then we count in between. We say 0.4 plus 0.01 is 0.41, 0.42, 0.43, 0.45. So this is where we have 0.45, and we go up now to being in line with 1.0, and it means that this point here is the point that we have to plot. So this is our point 0.45 and 1.0. Now our next point is 0.6 and 1.2. This is another one that's easy to plot because we look for 0.6 here. We go up till we find 1.2. That's right here. So we found our point, and then we can make our x. Now our next point is 0.7 and 1.5, sorry. Now we know that we don't have a 1.5, so we have to approximate. And we know we said here before that each of these tiny boxes is 0.02. So then we know we'll have 1.42, 1.44, and 1.46. Why am I saying 1.44 and 1.46? It's 1.5 we need. So let me just erase this here. Right, so we have 0.42, 0.44, 0.46, 0.48, 0.5. So this is the line with 1.5. I don't know why I'm saying 0.5. So if this is the point 1.5, it means we have to go across here and find 0.7. So let me make this a little bit smaller. So we go up with 0.7, which is in this line, and we make our mark at the intersection of 0.7 and 1.5. Now our final point is 0.8 and 1.7. So we do the same thing. We look from 0.8 and go all the way up, and we're looking for the point 1.7. I don't know why I keep saying 0 point something for every single point. So 1.7, how do we find that? We'll notice that we don't have 1.7 again here, which means we have to count and find where 1.7 is. Now we have 1.6 here and 1.8. So it stands to make sense that it stands to reason that 1.7 would be in the middle of those two. So then we can say 1.62, 1.64, 1.66, 1.68, 1.7. So then we go across now at this point 1.7 until we find the point where current is equal to 0.8, and we make our X, and that is our graph. So you see, everything doesn't line up perfectly, but that's how it goes sometimes. Nothing is ever perfect. We always have some discrepancy somewhere that causes some value to be a little bit off. Now our last step is to draw our line of best fit. Our line of best fit essentially is, if you're familiar with Microsoft Excel and you put the trend in the graph, so it is a straight line going through the graph that shows you like the general gist of the graph. That's what your line of best fit is. So it's going to be a straight line that will try to pass through all or most of the points. It's possible sometimes that it doesn't pass through any, but the line of best fit, you have to think of it, it's not like a dot-to-dot game where you're trying to connect the dots. It's really like an average of the points. So if you're drawing a line of best fit, let's say my line of best fit may pass here. We have some points on this side, we have some points on this side. So it's kind of balanced and it's showing the general area or the general trend of the graph. So it can take a little time, and I'm going to ask you to be a little bit patient with it. Let me remove my highlighted mark. So be a little bit patient. Like, I'm going to try to be patient right now and draw this line of best fit. Now you'll notice that you'll have to bring your ruler and angle it around a little bit. See, okay, where's the point that makes the most sense? This is why it makes sense to have a transparent ruler, or at the very least a translucent ruler, well, a sort of see-through ruler, so that you can see to know how many points you have on each side of your line of best fit. Now I'm not going to get a perfect line, and it's even trickier for me here compared to if I was doing it on paper, so I'm going to leave my line of best fit somewhere around here. It doesn't look very balanced though, so maybe while I'm teaching you all how to do a line of best fit, I may do a horrible line of best fit here that you all maybe should not follow, but we'll see how it goes. So this is where I am putting my line of best fit. So I would advise you try to always let it cut the axis and then go straight up to the other side of the graph. So I have my graph here. I put my pencil down. Where's my ruler moving? I think I will accept that there, even though it really isn't a good line of best fit that I'm doing there. So let me rotate you a little bit more this way, and I think I'm going to keep you there and draw my line of best fit. So you see let me move my ruler now, and that is my line of best fit. It isn't such a wonderful line, but if you look at it, you'll see it passes through 3 of the points, passes through the origin, it passes through here and here, and then here we have 2 that are really close to it and 2 that are a little bit further off. So it's just showing us the general trend. So this is how you plot your graph, how you plan from beginning to end, and you plot your entire graph. Now after this, you may go on to find the gradients and whatnot, and we're going to be covering all of that in our next video. So that's it. We looked at how to plot a graph, why we use it, and how we do everything from beginning to end. I hope you all find this video informative. Remember, there are the links below for plotting practice if you need it, and remember to look out for the next video where we'll be looking at gradients. So I hope you all enjoy the video. Remember to stay safe and be kind to yourselves. Thanks for watching. Bye bye. Have a great one.